Okay, so you got the vector n, and you project it onto the vector k, and you get these two similar triangles, as I alluded to earlier. I didn't go anywhere with that before, but I'm going to go there now. Okay, these two triangles are similar. Now, the question then is, if I bring this yellow triangle out here, here's the right angle in the orange triangle. We know that the hypotenuse of the orange triangle has to correspond to the hypotenuse of the yellow triangle. Okay, now I project the normal vector onto the k vector. And since the k vector has magnitude 1, that projection is just has magnitude n dot k. Well, magnitude is the magnitude of n dot k. So n dot k is here. Projection of your n vector onto your k vector. The question then is, which side of this triangle corresponds to which leg of this triangle? Which of the legs that meet at the perpendicular correspond to which legs of this triangle? Now, I drew a couple of other triangles where it's obvious which leg corresponds to which. If my segment is here, then my normal vector would be here, and my projection would look like this, and my triangle here would look like this. So it's clear which side is the shorter side, which leg is the shorter leg. This leg and this leg, which means that the same is going to be true here. This leg and this leg are going to correspond. So you're going to have similar triangles. This leg corresponding to this leg. Now over here, we can calculate the ratio between the hypotenuse and this leg. Okay, and that's just n dot k, which is, magnitude of n dot k would be the length of this leg, and magnitude of n is the length of the hypotenuse. So the ratio is magnitude of n divided by the magnitude of n dot k. So over here, the ratio of this to this is just magnitude of n divided by magnitude of n dot k. That works on this triangle as well as it did here, where this is the leg that you multiply by this factor to get your hypotenuse. Now you need to work that out. You need to think about the trigonometry, about the properties of the dot product. People seemed a little shaky just with dot products. And I really need to be a little further along with dot products than that. Anyhow, this then implies for a cylinder that has the same cross section in any plane parallel to the YZ plane, it implies that the area ratio of a rectangle on the surface to the shadow below that rectangle, to the corresponding rectangle in the XY plane, this is going to be your ratio. Okay? So there's your area ratio. The area above your area increment is going to be magnitude of your normal vector divided by n dot k times your area increment. Okay? This is the area on your surface. This is the area down in the XY plane. It follows then, with some dots here, that the area of your surface would be the integral over the region in the plane of this magnitude of n divided by magnitude of n dot k times your area increment down in the plane. Okay, again, R is the region in your XY plane. Now to get from here to there, there are some details we kind of had to gloss over. What if this isn't parallel to your x-axis? In other words, what if your cross-section is different for different values of y? It's taken care of. That's the best I'm going to say right now. This is the ratio for the same reasons that this works. Okay, so right here is how you get the area of your surface. So the surface area of the region that we were asked to find, and that would be above this square, where x goes from 0 to 1/2, y goes from 0 to 1/2, is going to be the integral over that region of magnitude of n divided by the magnitude of n dot k dy dx. That's your area increment, and the square over which we're doing this integration has fixed limits on x and on y, so it's not a complicated region. Okay, now here we calculated the area of the surface above the triangle. Okay, here we do the same thing by an integral, because when you do an integral, there are two steps. You figure out what happens on a typical increment, which could be this, or it could be this. And this will give you the same result as this if you parameterize the plane, the plane that we used here. We're integrating this quantity over the triangle that goes from x goes from 0 to 1 and y goes from 0 to 1 minus x. That's the triangle described in the xy plane. So if we have the xy plane here, that's the triangle that goes from here to here. So x goes from 0 to 1, and for any given x, y goes from 0 to 1 minus x. If we do that integral of the square root of 7 over 2 to get the area of this surface above that triangle, the integral is going to look like this. Y goes from 0 to 1 minus x, x goes from 0 to 1, and on every one we're multiplying this area in the plane, delta y by delta x, by the square root of 7 over 2, because that's the way the plane is angled with respect to the plane, to the xy plane. Okay. Well, if we do that integral, we get this. This matches this. So we do this because the square root of 7 over 2 applies everywhere for every delta x by delta y region down here in the plane. Or we can represent it by an integral as so. Okay. So what we've done is we've gotten the expression for typical interval, typical area increment. We've described the region, and we simply integrate over the region the area ratio, square root of 7 over 2, just as we would do the same thing for a different function, integrating the magnitude of n over the magnitude of n dot k with respect to area. So if we had another function, another surface, a sphere say, we would replace the square root of 7 over 2 ratio between area down here and area up here by whatever that happens to be at a typical xy point. And we're going to do that down here.